Hi everyone, my name is Ethan Genter. Thank you for attending this session. Today I'm going to be talking to you about the regularity of detonation cellular structures and a recent study my colleagues and I did looking at hydrocarbon mixtures. Before I start, I'd like to thank my colleagues who helped on this project, Jackson Kennedy, Cinnamon Sipper, Amitesh Jayaraman, Nicholas Montes, and our professor, Wang. The cellular structure of detonation waves has of course been extensively characterized throughout literature. Several studies have been conducted looking at specifically what gives rise to the regularity of these structures, and despite no governing mechanism having been established, the degree of cell irregularity has been observed to be impacted by a combination of chemical and gas dynamic properties. I'm showing two such observations here. On the left is a study by Professor Radulescu's group looking at the influence of incident Mach number and the gas dynamic parameter of gamma on Mach stem bifurcations. The plot shows results from inviscid simulations where Mach stem bifurcation is observed as a function of both gamma and Mach number, showing an expected onset of irregularity due to Mach stem bifurcation around a gamma of 1.3, consistent with several experimental observations. On the right is a 2D numerical study done by Gamizo and Professor Oran and colleagues looking at the influence of the effective activation energy on cell regularity and accompanying fluid structures. The top set of numerical subfoils for a low effective activation energy display a very regular structure compared to the more irregular structure produced in a simulation of higher effective activation energy. To leading order, both of these studies highlight a parameter hypothesized to influence cell regularity. The gas dynamic parameter captured by the space ratio of specific heats of the von Neumann state, and the chemical kinetic parameter captured by the effective activation energy. Now, a challenge in studying the independent effects of gamma and effective activation energy is that they are difficult to isolate experimentally. This challenge was recently overcome by a collaborative work between our group and UConn, which looked at hydrogen-oxygen mixtures. On the left, I'm showing a parameter space plot of effective activation energy and gamma with accompanying classifications of irregular and regular mixtures for 3 studies. The regular mixtures are open symbols and irregular mixtures are filled-in symbols. In the hydrogen study, they varied both effective activation energy for a fixed gamma and gamma for a fixed effective activation energy. The isolation of these two effects was enabled through the use of dopant levels of ozone. On the right, I'm showing a plot from a separate study from our group looking at the effect of ozone on the Z&D profile of a hydrogen-oxygen detonation. The red curve denotes temperature and the blue denotes thermicity. Solid lines define those mixtures without ozone addition, and dashed lines define those with 3000 ppm of addition. Clearly, there is a significant effect on induction length with no significant effect on the exothermic length. Moreover, what was found is that there was no significant effect on other thermodynamic properties like CJ speed or gas dynamic properties like gamma. Coming back to the hydrogen study, what this study saw through independent variation of gamma and effective activation energy were results consistent with previous numerical and experimental studies, such as the work of Radulescu, Gamizo, and Oran on the previous slide. Namely, the effect of gamma alone was shown to increase irregularity for values smaller than 1.3, and for a constant gamma, the effective activation energy was found to increase irregularity monotonically. Now, what's unsatisfactory about this kind of study is that we have to explore 2 independent parameters as opposed to a single parameter describing cell regularity. Moreover, these parameters don't capture important properties of the detonation, such as heat release. To explore how we might be able to develop a single parameter that can capture these properties, let's first look at a snapshot of a regular cell. Here we have the outline of a cell traced by 2 triple points. Each triple point exists at the confluence of both the neighboring shock, the Mach stem, and the resultant transverse wave. In a perfectly regular cell, as the Mach stem sweeps out the cell path, we expect that the Mach stem should travel collinear with the direction of the global wave propagation, represented here by the blue dashed line. Now, to obtain an irregular cell structure, the necessary and sufficient condition for irregularity is that the cell not be aligned with the direction of global wave propagation. So the question is, how do we achieve this misaligned cell? One possibility is that we have a temperature difference across the 2 triple points. So for some temperature perturbation, we would expect that we would have a difference in the local rate of reaction. The difference in local rate of reaction leads to cell asymmetry, which would be expected to cause a deviation in the angle of the Mach stem propagation, and therefore a change in the cell angle itself. This is assuming, of course, that the angle of the cell is correlated with the direction of Mach stem propagation. Now, higher effective activation energy mixtures will be more sensitive to this temperature perturbation and would be expected to amplify the perturbation as compared to lower effective activation energy mixtures. In an ensemble of cells, we will have a distribution of these cell angles, and what we're interested in is the standard deviation of that distribution. This is because the standard deviation will be descriptive of how collinear cells are with respect to the direction of global wave propagation, and therefore descriptive of regularity. What we would expect is that higher effective activation energy mixtures will have a larger variation in cell angle, so for slow kinetics, which will amplify temperature fluctuations, we will have a larger standard deviation. Therefore, phenomenologically, we would expect that the standard deviation of cell angle is related to the sensitivity of kinetics to these temperature fluctuations. This relation will of course have some to be determined power of n, and note here that in the same spirit of using a global effective activation energy, we also normalize our temperature fluctuations by the temperature at the von Neumann state. So through similarity, we can additionally relate these local fluctuations in temperature to local fluctuations in Mach number in the small fluctuation limit. Combining these results, we obtain the following, what we'll call the cell perturbation model. And what this shows us is that slower kinetics are expected to amplify local perturbations, equivalently temperature or Mach number fluctuations, and lead to irregularity. This expression using a singular quantity for regularity makes sense for a couple of reasons. The first is that it now captures the effective heat release through the CJ Mach number equivalently through the temperature at the von Neumann state, while also capturing how quickly that heat is released through kinetics. Additionally, this expression makes sense in limiting cases. So if MCJ is low, we have very little heat release, and we have a weakly choke detonation for which we would expect a very irregular cell structure, thus a higher variation in cell angle. For extremely high Mach numbers, we would have a very high heat release, and we would not imagine the presence of a cell structure at all for such a strong blast, and therefore no variation. For high effective activation energy, we would have extremely slow kinetics, leading to large irregularity. And for low effective activation energy, we would have infinitely fast kinetics, giving a 1D CJ-like detonation structure in the limit of 0 cell size. Now, the objectives for the rest of this presentation and study will be first to develop a new measure and model for cell regularity based on Mach stem propagation angle, and second, to experimentally test the new model for cell regularity using soot foil measurements from hydrocarbon and hydrogen detonations. I'll begin with our experimental setup. All experiments were carried out at the Stanford Linear Detonation Facility. The facility used for these experiments is comprised of two sections, a driver section and a test section. The driver section is a 1.2 meter long stainless steel tube, 73 millimeters in diameter, where we will initiate our detonation. The test section is a 2.4 meter long polycarbonate tube, 32 millimeters in diameter, where we'll confirm we have obtained a relaxed detonation and subsequently measure the cell pattern. There are two forms of diagnostic on the setup. The first is time of arrival detection used for calculation of the global wave speed. This is accomplished with 3 pressure sensors on the driver section and 24 photodetectors on the test section. The second is, of course, our soot foil placed at the end of the test section. We use a polyester foil 60 centimeters in length and 10 centimeters in width. For a single experiment, we start with vacuuming of the entire tube. Once vacuumed, the tube is filled with a composition of interest to an initial pressure of 40 kPa and initial room temperature. Once filled, we isolate the tube completely, and then we ignite within 30 seconds. Once we have observed a successful detonation, we can then analyze the accompanying soot foil. Here I'm showing an example soot foil for a hydrogen-oxygen mixture. Once a cell structure has been identified, we extract 3 geometric quantities. The first two are the cell length and cell width, and the third one is a new quantity, cell angle, for which we have assumed to be correlated with the direction of the Mach stem propagation within a cell. This allows us to probe the variation in the Mach stem propagation angle through the measurement of a soot foil. Here I am showing the parameter space for effective activation energy and gamma again with the same previously studied mixtures, and as a reminder, the filled symbols correspond to irregular mixtures and the open symbols correspond to regular mixtures. For this study, we have constructed 10 mixtures that isolate the effective activation energy or gamma independently. Their CJ and Z and D parameters are shown in the table at the bottom. Those mixtures that we designed look like this. And as you can see, we have both isolated the effective gamma and the effective for a fixed effective activation energy and vice versa. The 8 mixtures used in both of these parameter sweeps are hydrocarbon mixtures, either methane or ethylene, as shown in the table below. Additionally, there are 2 hydrogen mixtures here coincident with mixtures used in the previous study from our group in the same experimental facility, allowing for comparison and validation of experimental procedures and measurements. This parameter sweep enables us to test the perturbation model in the limit of more irregular mixtures, while independently varying gamma and effective activation energy. Specifically, the variation in effective activation energy is at a constant gamma equal to the previous hydrogen studies. This will allow us to compare the model to hydrogen as well. Before we touch on the results, a key question we had in this study was what is the minimum number of cells required to achieve statistical convergence? For this, we selected one of our 10 mixtures, mixture 2, to test. On the left, I am plotting the probability density of cell angle for this mixture. The top plot shows the probability density of an original measurement for a total of 50 cells across 2 successful experiments. The bottom plot shows measurements done for 7 additional stood foils from additional experiments using the same mixture, now for 494 cells in total. We can see by comparing these two plots that a significant increase in the number of measurements gives nearly the same mean and standard deviation. Of course, one would expect this from the central limit theorem, where the sampling distribution converges rapidly to a normal distribution with an increasing number of samples, regardless of the variable distribution in the population. If we take this study a step further and look at the distributions of our 7 new stood foils, we can see that by 50 samples, the mean and standard deviation of theta have already converged. Here I'm plotting the mean and standard deviation of individual stood foils measured in the convergence study. The filled circles define the mean, with the bars defining the standard deviation, and the open circles define individual measurements. The red case defines the initial measurement of 50 cells, and again we can clearly see that the standard deviation of each stood foil is very close to one another. To further ensure that we have converged statistics within 50 cells, we can take these new measurements and cross-sample across stood foils, randomly sampling 25 measurements from 2 different stood foils to test the minimum criteria of 50 cell measurements. This is what I'm plotting on the bottom here, where each unique permutation is an instance of cross-sampling. Again, we clearly see that the mean and standard deviation is closely sampled, and as an additional check, we can look at the sampling distribution of these permutations. If we have converged statistics, then the sampling distribution of cell angle should be approximately normal. When we plot the probability density of these permutations, as expected, this is exactly what we see. When we look at the sampling distributions of other mixtures as well, we have the same result, meaning that our minimum criterion of 50 cell measurements satisfies our need for convergence. Having established converged statistics, we can now analyze the results of our cell measurements. On the left, I'm plotting the standard deviation of cell angle as a function of gamma. All mixtures have a constant effective activation energy of 8.75. This plot shows no distinguishable trend in terms of the variation in cell angle with respect to gamma. This result may seem contradictory to previous work from Radulescu and the hydrogen study, where the effect of gamma on cell regularity was found to increase irregularity beyond a gamma value of 1.3. However, it's important to note that these results are at elevated effective activation energies. This means that the effect of gamma may be amplified or muted depending on influence of chemical kinetics. This also means for our derived relationship that the implicit dependence on gamma is likely weak for moderate to elevated activation energies. If instead of isolating gamma, we isolate effective activation energy, we obtain the following results. Here I'm plotting the standard deviation of cell angle as a function of effective activation energy for a fixed gamma of 1.27. The orange squares define measurements taken from stood foils produced in this study. So these are all hydrocarbon mixtures. The mixtures defined by the blue circles are cell angle measurements taken by us using stood foils produced in a previous hydrogen study. What is clear is that there is a strong, nearly linear increase in irregularity with increasing effective activation energy. This increase in irregularity with increasing effective activation energy is consistent not only with the hydrogen study, but also previous work looking at the influence of effective activation energy, as is well known. Moreover, this linear dependence is consistent with the model developed earlier. However, in order to compare the results directly to the model, we must compare our standard deviations in cell angle to a normalized or CJ Mach normalized effective activation energy. That is the parameter that we found earlier. When we plot this comparison, we can see that all of our data collapses and is in agreement with the model. Moreover, we see that in the limit of infinitely fast kinetics, we obtain the expected result for an equivalent 1D CJ detonation. This is for an effective activation energy of 0, equivalent to infinitely fast kinetics. We expect the standard deviation of cell angle to be 0 in the limit of 0 cell size. This linear increase in regularity with respect to our single quantity of E of epsilon I over mCj also tells us that our power of n in the perturbation model is actually 1, giving the following relationship. Physically, this result indicates that the regularity of detonation cellular structures is dictated by local sensitivity of chemical kinetics, which give rise to perturbed Mach stem trajectories. Now, such a result is too good to be fortuitous, and in fact, we can explain this both physically and mathematically. Let me first discuss the physical interpretation here. It's been widely observed that at the intersection of two triple points, we have high-speed collimated flow. This corresponds to a local jetting phenomenon. A recent soon-to-be-published collaboration between Stanford, UConn, UC Irvine, Ottawa, Duisburg, UCF, and Texas A&M has indicated that these microscopic high-speed jets impact early cell formation by driving the Mach stem. Here I'm showing two plots. On the left, a 2D numerical simulation of a hydrogen-oxygen detonation propagating from left to right, the color bar indicating velocity relative to the CJ speed. We can see high-speed jets present at the birth of each of these new cells. On the right is a zoomed-in view of a cell in the early stages of formation with the flow field colored to show vorticity. This image gives us an idea of how these jets are formed and drive the Mach stem. Briefly, this process looks like this. Shear layers emanating from the triple points come together to stagnate, forming a backward and a forward jet that is accelerated by a pair of neighboring vortices. This jet then acts as a virtual piston, pushing the Mach stem forward. Therefore, the direction of the jet is correlated with the propagation of the Mach stem. Now, with an understanding of what hydrodynamic mechanism impacts the propagation of the Mach stem, we can then look at how sensitivity to kinetics should affect the jet direction, specifically through their effect on the neighboring vortices. First, let me again show a regular cell. Here I've drawn the flow path. We have our shear layers stagnating to form a backward and a forward jet, which is accompanied by neighboring vortices. For a perfectly regular cell, these should be the same strength. Now let's look at an irregular cell. If again we have a local temperature perturbation, we will have a difference in the local reaction rate. For a higher temperature, we will have slightly faster kinetics, and this will lead to a change in the strength of the associated vortex. This difference would lead to one vortex with a slightly higher angular velocity due to gas expansion. Here we assume a power law behavior for that kinetic timescale or that associated kinetic timescale, but this ultimately will not matter for our final result. We can see that any difference in vortex strength will necessarily give rise to a difference in the vertical component of the velocity of the jet. Assuming rigid body rotation, we can describe this difference and then geometrically relate our difference in angular speed to the angle of jet deflection. Because we can relate our difference in angular velocity to a difference in kinetic timescales, as shown by the first equation, we can relate our angle of jet deflection to a difference in kinetic timescales as well. Lastly, recall that we want to take an ensemble average of this change in angle across many cells, so we will have a distribution of angles. Again, we are interested in the standard deviation of the cell angle. Because we've related our jet deflection to differences in kinetic timescale, which fundamentally arise from temperature perturbations, we can directly relate temperature fluctuations to the standard deviation in cell angle. Equivalently, we can construct a relation for the fluctuations in Mach number and recover the same perturbation model we tested earlier, here just adding the fitting constant alpha. Again, this expression gives us a single quantity to describe regularity that isn't only dependent on effective activation energy and the ratio of specific heats, but also the heat release. To conclude, let me highlight some of the key conclusions from this study. The first is that the effect of gamma is small for sufficiently high activation energy mixtures. We also learned that an increase in effective activation energy significantly increases cell irregularity, generalizing earlier results to hydrocarbon mixtures. Lastly, we saw that the governing mechanism for cell regularity is dictated by local sensitivity of kinetics, which give rise to perturbed Mach stem trajectories. What this expression tells us, this one on the bottom left, is that given some temperature fluctuation, it's the response of kinetics which determines the resulting regularity we measure through soot foil angles.